Hi guys, in this video we are going to take a look at applications of using the method of Lagrange multipliers in finding the dimensions of a box with minimum surface area and a given volume. So usually a lot of students having trouble figuring out which function is f and which function is g. So when you're dealing with method of Lagrange multipliers, you are trying to minimize or maximize the f function subject to a constraint, and usually we want the g of xyz equals 0. Now, what is is it that we're trying to maximize or minimize here? So it says, what is the minimum surface area? So it looks like the surface area is the one that you are trying to minimize, right? And so then your function f should be the surface area, okay, not the volume. A lot of people put that in the f. That's not correct. So imagine that this is your box, right? So I'm just going to draw a rectangular box, and it has dimensions x, y, z. So it'll look like something like this, right? So here we have x, here we have y, here we have z. And so we're trying to minimize the surface area. That should be, okay, so first look at the bottom. The bottom area, because it's a rectangle with length x and width y, that's just going to be x times y. But it'll be exact same thing for the top. So that will become 2xy for this surface area. Now, what about the right and the left? So if you're looking at the right side of the box and the left side of the box, so dimensions are yz, and we have two of them, so that'll become plus 2yz. And then for the front and back, I'm not going to draw it because it'll just be too busy, but that's just going to be xz. So we have 2xz. Okay, so that would go into your f function, which is what you are trying to minimize here. Okay, then g is the constraint. Well, what is the constraint? We are told that the volume is 1331, and the volume of a box with length, width, and height xyz is just going to be the product xyz. So we have the constraint xyz has to be 1331. So writing that so that 1331 is moved to the other side, we're going to get xyz minus 1331, right? So that's our g function. So that is going to be equal to 0. That's the constraint. So then method of Lagrange multiplier says that we are going to have to compute gradient of f and gradient of g. So let's look at gradient of f. Now we are adding terms here. And so when we take the derivative, first we're going to take the derivative with respect to x. That means that you have to take the derivative of each term and add them up. So for 2xy, you think of 2 and y as being numbers, so we keep them. That's like a constant multiple. Plus 2yz with respect to x will be 0 because there doesn't have an x. And then plus 2xz with respect to x, that's going to be 2z. So that's the x derivative. Similarly, for the y derivative, we're going to wind up with 2x plus 2z, and 2xz will disappear. And finally, for the z derivative, 2xy will disappear. And then we'll get 2y plus 2x. Okay, so that's what I will type in here. And 2y plus 2x. Okay, so this one is going to be very easy because that just has one term. So with respect to x, that'll be yz. With respect to y, that'll be xz. Notice there is an extra equal sign I need to delete. Okay, and with respect to z, that's going to be xy. All right, so we did that. Now, how are we going to solve for our x, y, and z? Well, that's going to be kind of lengthy, so bear with me. What we have to do is find this by method of Lagrange multipliers. It says that wherever maximum and minimum happens, the gradients, gradient of f and gradient of g, should be proportionate to each other. And this constant, the proportion constant or whatever, is called Lagrange multiplier. So the reason why I don't like the way that most teachers explain this material is that they get bogged down with this lambda. They're trying to solve for it, but we don't really need it here. Here's why. What they're really worried about, because they are like true mathematicians and everything, and it's because they're worried about what if x, y, and z are not, like what if they're zeros? And division by zero is not allowed. However, In application problems, x, y, and z are not going to be zeros, okay? Let me break something to you. The sides of a box are not going to be zero, okay? So you don't have to worry about this lambda thing. All you want to worry about is the gradients being proportionate to each other. So what you want is set up a proportion, okay? And so we have, I'm just dividing the x by x, the y by y, and the z by z. And if you think that this is seems like really intimidating, actually this is not that bad. I'm going to show you a lot of stuff is going to cancel. So look at the first two proportions. So here we're going to cross multiply. We're going to get 2y plus 2z, and we multiply that by xz. And then we got 2x plus 2z, and we multiply that by yz. So if we distribute that, that'll become 2xyz plus 2xz squared equals 2xyz plus 2yz squared. Okay, now look at what happens here. Both of these have 2xyz, so we can just subtract them from both sides and that's going to disappear. And then we wind up with 2xz squared equals 2yz squared. And we can cancel the z squared on both sides and the 2 on both sides. And guess what we get? We just get y equals x. Okay, so that's the relationship. So we already know that the length and width need to be the same. Now, what else are we going to do? Okay, what else we're going to do is I think we can take a look at the first and the third term, like that. All right, so let's see what happens there. So again, we cross multiply. So we get xy, we multiply that by 2y plus 2z plus, oops, not plus, equal, okay, yz, and then 2y plus 2x. Okay, so what happens here? It better cancel. Lots of stuff has to cancel. So we get 2xy squared plus 2xyz. That's on the left. On the right, we get 2y squared z plus 2xyz. Okay, awesome. All right, so we do see that 2xyz cancels on both sides. And then we got 2xy squared equals 2y squared z. So guess what? Same thing happens here. The 2 cancels and the y squared cancels. And so what I wind up with is that z is also x. Okay, wonderful. Now we also have to worry about the constraint. And what was the constraint? So never move on until you use the constraint. The constraint said that x, y, z has to be 1331. But we now know that y is x and z is x. So let's substitute that. So we get like x multiplied by x multiplied by x. And that's really the same thing as x cubed. So that's 1331. Now this should be a nice number. So let's see if I can compute that. So if I do a cube root of 1331, that gives me 11. So that's great. Okay, so that tells me that x is 11, but so are y and z because they are the same. So I think the dimensions are just going to be very simple. So this box is going to be a box with squares for all sides. Now, what they want is also the minimum surface area, because remember we were minimizing the surface area. So we are saying that all other possibilities, and you can check that if you pick any xyz that will satisfy the constraint and plug into here, you will get an answer that's larger. So this is going to be a minimum, and you could check that. All right, but what is the minimum surface area? Well, that's very simple. We just have to plug in 11 into the surface area, into the f function. But each term will be the same. It's going to be 2 times 11 times 11. So we're just going to get 2 times 11 times 11, and that's 3 terms like that. So that's 726. That's going to be my surface area here.